Hi everyone, and welcome to this example video of the indented paths that we discussed on the last video. So we're considering an integral from minus infinity to infinity, as you can see right over here. And the first natural thing to do is to promote all the variables to the complex variable in terms of z, and the contour we're going to choose is something like this, because there is a singular point or a pole at z is equals to 0 or x equals to 0, however you want to call it, and you can see that there are no other singularities that is inside this contour. That means inside this region, this blue region. So the first thing we're going to do is that we're going to write out the residue theorem. This is just 2 pi I and the summation of the residues, right? However, residues come from singular points, and none of the singular points are inside this contour. That means this function e to the power I z by z is analytic through this region, through this colored region, and since there are no residues, no singular points, the residue is 0, so this is just 0, right? However, we're going to calculate this integral from this part. How? Because we're going to decompose this contour integral for this specific parts, that is from minus r to minus epsilon, from minus epsilon to plus epsilon, then from plus epsilon to plus r, and then on this bigger semicircle, and obviously this smaller semicircle is denoted by c epsilon. So let me just write that down. So this will be from minus r to minus epsilon. Here the whole thing is lying on the real x line. That means there is no imaginary component, so this will just be to the power ix by x dx. Then you'll have this plus epsilon to plus r part. This will also be the same thing. Now for the smaller circle and this larger circle, so we'll have this larger circle thing. Here you will have e to the power I z by z dz, and finally you will have this smaller circle c epsilon. Again this will be to the power I z dz, and this is equals to 0, right? So now what you're going to do is that you're going to take the limit epsilon goes to 0 and r goes to infinity. That's the limit we want to take. So let me just write that down, that this means this epsilon goes to 0 and we're going to take the limit r goes to infinity. And if you do that, you will see that the theorem we discussed on part B on the last video, you will see that this smaller circle will contribute a part like this. This smaller circle part, when this limit epsilon tends to 0, this will give us negative I, because this is on the clockwise direction. As we go from minus r to plus r, this is on the clockwise direction, that's why there is a minus sign. And since it encloses a semicircular part that is starting from here to here, the angle here is just pi, so you have minus I pi, and there will be some residue part that is coming from here, this function. So if you recall how to calculate residues, this will just be the residue for z is equals to 0 for this function over here, and if you calculate it, this is just e to the power I dot 0, which is equals to 1, right? So the residue is 1, that is c inverse c minus 1 is just 1, so this is just minus I pi. And for the bigger circle, we are taking this limit r goes to infinity, so the bigger circle part cr e to the power I z by z dz will be 0. Why? This is coming from Jordan's lemma that we discussed in one of our previous video, that if you have a function that goes to 0 when r goes to infinity, and that function have some exponential times exponential to the power I times some complex variable, this whole integration will be 0 when r goes to infinity. And obviously without Jordan's lemma, you can also refer to the maximum modulus principle. If you do that, then you will see that it's something like this, this pi r thing, and when this r goes to infinity, this guy goes to 0. this is just 0. Alright, so that's the idea behind this part going to 0. So we can see that this part is contributing minus I pi, this part is contributing nothing, this is going to 0, and the last thing is these two parts. And when epsilon goes to 0 and r goes to infinity, we will have something like this. That is, your instead of epsilon you will put 0, and instead of r you will put infinity. So minus 0 and plus 0 is the same thing. So instead of minus epsilon you will just put 0, and you will have a minus infinity over here. This is e to the power ix by x dx, plus you will have a 0 to infinity, because here you have a plus epsilon and epsilon is going to 0, that is this limit, and r is going to infinity. So that's why you put infinity over here. You will have this e to the power ix by x dx. This part was 0, it's contributing nothing, and this part is contributing minus I pi. So you write this contribution minus I pi and you equate it with the right hand side, that was 0, because there were no singular points inside this contour, inside this annular region, or a semi-donut like region, whatever you want to call it. And you see that this is just minus infinity to plus infinity, e to the power ix by x dx is equals to I pi, right? So we are technically done. However, if you decompose x into the real and the imaginary components in terms of the Euler identity, you will have something like this: minus infinity to plus infinity, e to the power ix will give you cosine x, x dx. Then you will have this minus infinity to plus infinity, there will be an I over here, sine x dx by x, and this will equals to I pi. So now you are going to want to decouple the real and imaginary components. That means equating the real parts, real part, you will get minus infinity plus infinity of cosine x dx by x equals to 0, because on the right hand side there is no real part, right? So the real part can be written as 0. So that's why the real part on the left hand side will be equal to the real part on the right hand side, and this is just 0. And if you equate the imaginary parts, you will have from minus infinity to plus infinity sine x by x dx is equals to pi. That's it. So though we are considering some integral like this, ultimately we found two integrals, that one of them involved the cosine x and one of them involved the sine x, and both of them are improper integrals. So this is how you can do your calculations with the indented paths, and I'll see you guys on the next lecture, and this will be it for today. Thank you.